Okay, so good afternoon, everyone. Welcome to APNIC eLearning web class. Today is the 31st of August. It's Wednesday. We call it as the eLearning Wednesday. And it's 3 o'clock in the afternoon from Brisbane in Australia where I'm doing this class. Now, the topic that we are going to cover is IPv6, particularly the security side of it. So it's IPv6 security. As I have previously mentioned, this is the first time that we are conducting this course. So I appreciate any feedback with regards to the content, whether it meets your your expectation and what you'll get out of this course. Now, a few things about myself. My name is Sheryl Hermoso. I work as a training officer for APNIC. I'm part of a team that conducts either face-to-face workshops or online courses on topics that are related to the internet community, particularly network security, IPv6, routing and BGP, DNS and DNSSEC, internet resource management, and all of those things. Now, this session is provided for free and it will be going on for about an hour. Just a reminder that towards the end, I will be asking you to fill in a survey. The link will be available at the end. So what are we going to cover for today? As I've said, this is IPv6 security. So some familiarity with IPv6 would come in very handy coming into this course. Hopefully, you have attended our previous e-learning courses on IPv6 or maybe one of our IPv6 workshops, where we covered the basics of the IPv6 specification. We have also covered the IPv6 addressing and subnetting, and a few things about how you will use them to do transition or to plan your IPv6 implementation. Now here, we will be looking more closely with the very first session, which is on IPv6 protocol specifications, and find out what are some of the issues, what are some of the difficulties when it comes to those protocols. We will look just very briefly at IPv6 operations to understand them, and from there, nitpick where are the possible issues. So again, our focus mainly is on layer 3. It's on the protocol itself and what are the differences in its operation as opposed to IPv4 and what are the possible issues with that. We will also look at scanning IPv6 networks, things like filtering, how we're gonna avoid those things. We have some examples for you. I'll show you some possible toolkits that can be used in a good way or maybe in a bad way, and some example attacks using those toolkits. At the end, I'll just show you very quickly some of the best practices in how you can secure IPv6. Now let's begin with IPv6 operations. We all know what IPv6 is, hopefully, coming into this session. It's a new protocol that kind of replaces or complements IPv4 because of its wider range of IP address. It uses 128-bit addresses, but when it comes to its how it functions, there are a few differences as opposed to IPv4. In v4, we use broadcast a lot. In IPv6, we don't use that. In IPv6, we have also introduced a few things such as extension headers, built-in security features, and the use of ICMPv6. So we rely heavily on ICMP. If you have, as part of your security practice, you tend to maybe block ICMP in IPv4, okay? In IPv6, you have to be quite careful with that. I'll look more closely into that a little bit later on. But these are just some of the things that you get out of IPv6. Now let's look at them more closely. This is the IPv6 addressing structure. As you know, it's composed of a 128-bit address, and half of that is what we call as a network prefix. This is where we do our subnetting. You are given a /32 from APNIC or maybe a /48 from your upstream provider. And from that, you subdivide those blocks into smaller ones, say /64, /56, and distribute them to parts of your networks or maybe to your customers. So this part from 0 to 64 is where you do your subnetting. Not sure if you can see my pointer there. So half of it is for your network subnetting. Now the other half is what we call as the interface ID. Now, as a best practice when you're doing addressing, 64 is the smallest that you can assign to a single subnet. whether you have 1,000 machines in that subnet, or maybe you only have 5, or maybe even less than that. /64 is the smallest for a single subnet. Why is that? We know the reason. One is, of course, the last 64 bits is what we use for interface ID or IID. So your operating system can assign these values automatically for you using some practices. Say one is what you call as EUI64, or particularly the modified EUI64. Once you enable IPv6 on an interface, you will automatically have an IPv6 address, a link local IPv6 address. It starts with FE80, right? Now the last 64 bits will be coming from your operating system, either as modified EUI64 or as a random number. When you say modified EUI64, it is based on your MAC address. So let's say, for example, this machine, okay, my MAC address is AABBCCDD, etc. So that's 48 bits. Okay, it will be expanded, divided into 2, and then somewhere in the middle you add an FFFE, and then you toggle the 7th bit whether it's unique or not. So that's how you form your last 64 bits, your interface ID. So what could be a problem with that? Just think about it for a second. For example, I am connected to a network here at the APNIC office. I can get a network prefix, right? A router, okay, or a DHCP server in this building is giving me a network prefix. However, the last 64 bits will be assigned by my own machine using my MAC address. And MAC address or physical addresses are unique only to this physical interface. So whenever I move from one location to another, let's say, for example, from APNIC, tomorrow I fly to, say, Singapore, or maybe I just move to my home network where it's using another IPv6 network. What happens is you will now have a new network prefix, okay, which is what that network is announcing, but your interface ID, or in this case, my interface ID, will stay the same. So it is a privacy issue. The interface ID part is assigned using your physical address, which is part of your machine. So when you move that machine physically within different networks, you definitely will have the same interface ID. So although that means it will be unique all over the world, okay, there will be no like very small chance or possibility of getting a, say, another machine or another host to have the same IP address. The problem there is it makes you somehow trackable, right? Me moving from one location to another means that someone can follow my traces, okay? Because your network prefix changes, but your interface ID does not. Now, a workaround with that is, of course, the use of random numbers. Most operating systems have support for that now. Even by default uses random numbers over EUI64. However, there are also other operating systems who uses EUI64. So I guess it's just a matter of it's up to you. It's your choice, really, right? If you're concerned about these things, about these privacy, then you might want to use random numbers. But that is one of the I would say limitation or weaknesses of the IPv6 specification itself. Another one that is related to addressing is being able to scan an IPv6 network. Now, there are a lot of myths that are going on around about IPv6, particularly with scanning. Everyone says that, oh, I'm okay. I don't really need firewalls. I don't need any protection in my network, even though I enable IPv6, because IPv6 network is just too big. Okay, it will take a very long time to scan it entirely. While that is obviously true, it is still possible to scan an IPv6 network by following some patterns based on a few different factors. Why is that? People tend to use, if you have attended our course on IPv6 address planning, there are some best practices there that tells you to use the first /64 block, okay, rather than the last /64 because you have less number of bits. So obviously, when you do your scanning, it starts from the very first block. There are also practices how you can use loopback interfaces and assign loopback interfaces using that first /64 or first /48 blocks. People also use vanity addresses. So it is possible to follow patterns in IPv6, therefore limiting the number or the size of the network that someone will have to scan. What else? What else have we got? In the next slide here, let's talk a little bit about IPv6 extension header. By the way, if you do have questions, please feel free to write them down in the chat. Now, what is an extension header? In IPv6, if you try to compare v4 and v6, there are some fields in the IPv4 header that they think are not really that important. They are used in some cases, but not in all packets. So what they did to make IPv6 make faster, to have better latency, is to remove some of those fields and then just add them whenever it's needed. So the base IPv6 header will have 40 bytes. Okay, it doesn't have those extra options, padding, and other fields that you find in IPv4. However, if you do need them, they can be added. It's called the extension header. Okay, IPv6 extension headers extend the functionality of the protocol by adding an extra header in between your base IPv6 header and the payload itself, okay, the IP payload. So for example, in this case, originally your IPv6 header is followed by the payload, or if you look at it from the upper layer, that's your TCP header and TCP segment. But if you are going to insert an IPv6 extension header, you will have something like this. You have your header followed by an extension header, in this case a routing header, followed by another extension header, a fragmentation header in this case, and then the last one here that follows is your actual payload. So what happens is you're inserting extension headers somewhere in between your IPv6 header and your actual data. Now you have a pointer, we call it as a next header field, that tells you what follows after this, meaning I can add as many extension headers as I want, and it doesn't matter because the last of those extension headers will definitely just point to my IP data. Okay, so a few things when it comes to IPv6 extension header specifications. The number of extension headers are not fixed, meaning you can have 0. Okay, if you don't have that, that's the first example over there. And you can also have more than that. The total length of the extension header chain is variable. It can be 2, 3, it can be 100. So that can be an issue. Okay, the order of extension headers are also not strictly implemented. There are recommendations. For example, some of the extension headers has to be at the very start following your base IPv6 header because it is read by different routers as you go along the path. However, it is again a recommendation, not a requirement. So you can pretty much move them around. So what are the possible issues here? Let's look at that in the next slide. If you are an attacker, how can you manipulate the extension header and use them to your advantage? Now, an attacker can manipulate this feature by looking at these possible things. 1, create an IPv6 packet, okay, with a long list of extension headers that can cause a denial of service attack to the router. So, in the previous slide, I told you that you can have as many extension headers as you want. So, the more that you have there, okay, it becomes a load to the router. If you have multiple IPv6 packets with very long extension headers, it will take time for the router to process them. So if the purpose is to attack that router and use up its resources, then by sending a few 100,000 IPv6 packets, it will succeed. That is a denial of service attack, right? Another thing is the lengthy extension header. Well, that's very similar to the first one. Could cause or could consume system resources or could even crash the host protocol stack. Now, going back to the first one there, long list of extension headers, it could also be that you are just adding so many of the same types of extension headers. Again, the purpose is to overwhelm a particular router. And then here you have could be used as an attack vector to inject malicious code. Now, this is very important because, like, going back here, you said that what follows, what's the content of this routing header? Okay, well, it tells you exactly what it is, but someone can use, say, a routing header or a fragmentation header, but input something else in it. Okay, and like a malicious code, for example, and that has happened in the past. There are examples of this being done in some environments. Okay, so the idea here is you are using that extension header so that even if you have, say, an IDS or an IPS somewhere, okay, it cannot detect the malicious code because it is considered as an extension header. It's not part of your payload where you have some signatures that you can check with about it. So as you can see, the idea about extension header is good, right? You have there, you're kind of like lightening up the load of your routers by putting some of those unnecessary stuff in the extension header and just adding them whenever they're needed. However, okay, attackers will always find a way to do malicious things like this. So that is also a possibility, and we've seen that here. Another one about IPv6, and this is somewhat of a myth. IPv6 is secure. Okay, I don't need to do anything. I don't need to add maybe extra encryption on my application layer because I'm implementing IPv6, and I heard from someone that IPv6 is secure. While it is true, there's some truth to it. Why? Because IPsec is part of IPv6. So if you're familiar, IPsec is a security protocol that is on layer 3, okay, is added as part of, well, as an extra layer of protection alongside your IPv4, right? Now, before we have had IPsec in IPv4, the original idea was that IPsec will be part of the IPv6 protocol implementation. And it is here. The reason we have IPsec and IPv4 is because it's taking a very long time to actually everyone to migrate into IPv6, and then we still need that security in the IP layer in IPv4. So IPsec is part of the IPv6 protocol, and it gives you, of course, those confidentiality and integrity needs that your data needs, right? So, however, please be aware that IPsec does not replace any standard network security requirements, okay, of any sort. So even though you have that end-to-end secure connectivity, if you've implemented IPsec on both ends, okay, because the other party can choose not to ignore those negotiations with IPsec as well. But even if you have that in place, okay, you still need to add protection on all other layers of your TCP/IP protocol stack. All right. Okay, I have a few more. Okay, here, let's look at this particular protocol in IPv6 that is used largely for finding neighbors, finding routers, and assigning IP address to hosts and network devices. It's called NDP. Hopefully you have some familiarity of NDP, but we will see from a security point of view how NDP has some weaknesses that is exploited in a lot of sense. And I'll show you some examples of how that's exploited. So what is Neighbor Discovery Protocol or NDP? I've mentioned earlier, and I think you all know, that IPv6 does not use broadcast, right? IPv6 uses multicast, okay? To find out machines, say if I am going to assign an IP address on this machine, I have to double check whether someone else is using that, and I'll use NDP for that. And if I want to assign an IP address here, okay, I will also use NDP to find out other neighbors or find out other routers that can give me a network prefix, okay? And then also do that for, again, finding out whether before assigning, it will be a temporary address, and before assigning, is there any duplicates within the network? So NDP is particularly used for these three main purposes. It's the same protocol, okay, but just very slightly different purposes. Stateless address auto-configuration is when you're assigning a linked local address to your interface, okay. Neighbor discovery, looking for other neighbors if you're sending data to a specific IP address, kind of like if you think about ARP, right? But ARP uses broadcast, so NDP it's kind of like equivalent in the IPv6 hood. We also have router discovery, looking for routers where I'm going to send my packets, okay, my gateway, or also getting IP address prefixes that I can use to assign a unique local address or a global address to my machine. And that is duplicate address detection. Now for all of these, NDP uses the ICMPv6 transport. That's why I told you it's important to understand when and what types of ICMPv6 you're going to allow or block from your network, okay? Because it uses ICMPv6 a lot. I'll show you which particular message types. It's this one, okay? It's 133 for router solicitation. So that's looking for any routers that will advertise a prefix to me. And then the response to a router solicitation message is an advertisement, router advertisement coming from a router containing a network prefix. We also have the combination of neighbor solicitation and neighbor advertisement when looking for other neighbors. And the last one is redirect for routers informing the host of a better hub going to its intended destination. So these are the 5 very important NDP messages that we all should be aware of. This is how it works, right? Just very quickly. Hopefully you already know this a little bit. So when a new host is turned on, okay, I have, say for example, this host. It will look for an IP. It will look in the network before it assigns an IP address. So when I turn it on, I will have a tentative address. Here I'm using EY64. Now, if I want to check, or before I actually assign this address, I will check the neighborhood, this link, whether there is a duplicate, right? If someone has used this. Obviously, we're using EY64, so ideally this should be unique, but every time that we assign an address, we always do this check. So you perform that. That means you're sending a neighbor solicitation message to the all nodes multicast address and then waiting for a response or neighbor advertisement. If nothing arrives, then we can say that it is therefore unique. And then we can now assign that linked local address to the interface. Now on the other side, we also want to assign either a unique address or a global address, so that this is globally reachable, because linked local addresses are only valid within the local link. It cannot pass through a layer 3 device, right? It cannot pass through a router. So what I'm going to do here next is to look for a router that will give me a prefix. It's called a router solicitation message. I'll send it to an all routers multicast group. So if there are 1, 2, or maybe 3 or more routers there, they're all listening to FF02::2. So I'll send it there. He will receive it, and then he will respond with an RA message, router advertisement. And then from there, it contains the network prefix only, and I will assign the first 64 bits with the network prefix plus my own interface ID or a random number if I want that. So, but basically, it's a network prefix plus the interface ID. So that's just an overview, right, of how NDP uses those messages, router solicitation, router advertisement. neighbor solicitation, and neighbor advertisement. So how can we or an attacker use this? Let's look at NDP attacks. Okay, if you have a good understanding of these messages of NDP, right, it's easy to grasp these types of attacks that I will be showing you next. But I have a few and I have some examples. Now there are different types that are related only to neighbors. A neighbor discovery, wherein you are going to either spoof or do a DOS attack to a particular neighbor. Another one is targeted towards the routers. Maybe someone will pretend to be a router, okay, advertising a prefix, or we're sending a lot of router advertisements to a particular host. We call it as RA flooding or rogue router advertisement, rogue RA. Note that actually anyone can send an advertisement. I can run a program in my machine and announce a route advertisement. So there is a possibility that that's not the prefix that's supposed to be assigned for that link. However, okay, since I announce it, someone will receive it. He might use it for that interface. And what's the result? Okay, it can be as simple as he cannot access the IPv6 network because he's using a wrong prefix. Or he may be announcing a lot of them, therefore overwhelming that particular host. So things like that. Now let's look at some of the examples. Before we do that, the examples that I'll be showing you are using one of these frameworks. There are frameworks out there that are available. They can be used for just testing your network perhaps, okay, whether you have these vulnerabilities and stuff, or it can be used by attackers as well. Okay, so it's a double-edged sword. It's a tool that's out there that can be used to perform IPv6 attacks. Now, the reason I'm telling you this is because I want to show you some examples that this is actually possible to happen, not just in the books. So you can look them up. It's THC-IPv6 is probably the most common one, followed by SI6. They have this really nifty tool called IPv6 Toolkit. And another one that's also kind of like based on that is the Chiron IPv6 attack frameworks. So I think the examples that I'll be showing are either using the first two, THC or the SI6. These are some of the commands that they have there. Okay, now I'm not going to go through each one of them. However, just please note that, see, what are these commands and what are the possible things that they can do. A live 6 is for looking for live interfaces that are using IPv6. So it can be used for looking for possible attack targets. Okay, after that, you will perform a more active type of attack. Say, do a redirect or do a spoofing. Okay, you can send a fake prefix using fake router 26. You can send a lot of send packets, that's THC sync, and things like that. So these tools are readily available for anyone who wants to use them. Similarly, for the SI6 toolkit, they also have a few commands within this framework, within this toolkit, that someone can use. Again, I'm not going to go through the details, but you can look at them up yourselves. Now, what can we use with these tools? The very first one, which I kind of have discussed a little bit in the beginning, is scanning for IPv6 networks. Now, you don't want to scan networks, particularly IPv6, manually. You want to code them and it does it for you. And even if you're running code, again, it still takes time to find all those live machines within an entire /32 or /48 block. But again, based on different patterns, it's easier. And using these tools, okay, can give you some really nice output within just a few minutes or maybe within just a few seconds. What are the things that are commonly done by people? People use easy to remember addresses. People use vanity names. So, for example, if my organization uses, maybe even Facebook, for example, they use vanity address. So if I can form my company name using the hex digits, then I would probably try and do that, right? Or maybe some just common words, beef, cafe, fate, etc. are normally used. So you can have a search for only those vanity words. You can also search for, if you're already familiar with the IPv4 addressing scheme of that network, you can use those IPv4 addresses, okay, because they're generally used as the last 32 bits of different IPv6 address implementations. Okay, loopback addresses, as you know, uses your network prefix, say 2001 DB8, followed by the last digit, colon, 1, colon, 2, colon, 3, etc. Those are the typical loopback interfaces assigned. So you can easily do a scan looking for live routers using these loopback addresses, as long as you know the network prefix, say /32, that's assigned for a particular network or a particular organization, and it's very easy to find that out. Now have a look at RFC 7707. It's got some really nice things about how you can perform network reconnaissance using IPv6. I think RFC 7707 is an update to an older draft or older RFC that kind of tackles that a little bit, but it's used for network scanning. So this is the more updated RFC that discusses about different types or different ways to do network reconnaissance in IPv6. So have a look at that. Now, using the tool, so here we use DNSDic for the DNS dictionary, and then Alive26. As you can see here is an example. Okay, I use a combination of DNS, so run that first, okay, and look for any mapping in the DNS for IPv6 prefixes. I'm essentially looking for quad A records in the DNS server, okay, doing queries onto that server and looking for possible targets. Which among those machines or hosts are using IPv6? And then from there, I'm one step closer to performing an active attack. And from there, okay, once I found out all of those mappings, I can use Alive26 to show any of these addresses that are actually live and up for that particular segment. So using still in NDP, right? So how can we perform a denial of service attack with that? So you're familiar with duplicate address detection or DAD. What happens is, before I assign a prefix, I will have to check the network whether this IP address has already been used or assigned somewhere else. So what I'm going to do, before I assign, I'll check, is this address unique? How I do that? Generally, I will send a neighbor solicitation message towards that link, towards that LAN. Now, if I have an attacker also connected to that LAN, I will just reply that and say, hey, this address is already taken. Whenever there is a neighbor solicitation message coming in, I will have a response, particularly for that NS message that says, no, you can't use it because I'm already using that IP address. So what you're doing is you're now, okay, trying to stop this machine from having an IPv6 address. This is an example of how you can do that. This is again another tool. It's DOS new IP6, which prevents any new IPv6 interface that comes up. This new interface will start sending a neighbor solicitation message, and I will always have a response to that so that he cannot get anything. So see that this is when I'm running it, okay, and I'm spoofing a lot of IP address. Whenever I see a neighbor solicitation message, I will spoof the packet and respond with an NA using that IPv6 address. So what happens, I don't have the any screenshot here, but what happens is my interface now, as from the victim machine, okay, cannot get any IPv6 address at all. So you cannot connect to the IPv6 network. Another one is neighbor discovery spoofing. So what happens here, again, we're still using neighbor solicitation and neighbor advertisement messages. But what I'm doing here is I'm looking for a particular neighbor so that I can send a packet. Right? So I'm looking for host B. This is host B's IP address. However, I need to send that on layer 2, so I need to know the MAC address. So I'll send a neighbor solicitation message going to that link, looking for the link layer address of host B. Now what the attacker will do again is he will send a lot of spoofed neighbor advertisement messages. I'm saying that for this IP address, this is the MAC address. This is my MAC address. So meaning everything will now be sent to him rather than the original recipient. How is that performed? Another tool that's available out there is Parasite 6. We normally call it as an ARP spoofer for IPv6 because although we don't have ARP in v6, right? We are all familiar with what ARP spoofing is. And it does the similar thing. It redirects all your local traffic to that particular attacker, okay? Because he responds to neighbor solicitation requests with his own fake MAC addresses, okay? So this is an example when that is implemented in my Linux box. So I spoofed, see here it says neighbor solicitation interceptor. So whenever a neighbor solicitation message comes, so it's the same as the previous example, very similar. Okay, any neighbor solicitation, I will respond with my own with my own MAC address so that traffic will come my way. Another one is rogue RA. Now here we're moving into router solicitation and router advertisements, okay, related to router spoofing and things like that. So what is router solicitation? I need to find a router in the network that can give me a prefix, right? Because again, I can have a link local address automatically, but that doesn't get me anywhere. I can only connect to machines within my local network. But generally, what we want is for me to be able to connect to the rest of the IPv6 network, maybe just within my own organization, or maybe in the IPv6 internet. So for that to happen, I need to have a unique address or a global address. So I'll look for a router to give me that network prefix that's assigned for that link. So I'm going to do that, client sends router solicitation. However, if there is an attacker somewhere there, okay, he will act as a default router. Therefore, that only means that, yeah, I'll just act like a router and send router advertisements for any router solicitation that comes in. Okay, I will use my own IP, I will use my own network prefix, which means that all traffic will now go to this attacker rather than to your intended default router. Okay, and as I've said earlier, anyone can actually act as a default router. From my machine, I can run a router advertisement, announce a prefix, and voila, traffic will be going my direction. So these are very possible to happen within the network. So attacker can now intercept, listen, modify the packets coming from host A or any other hosts that are within this network. I can be nice and just intercept message, but then still redirect the traffic to the actual default router. So you never know, someone is reading or intercepting messages. That's man-in-the-middle attack. Okay, but because you still have access to the IPv6 network, you can still do your normal internet stuff. But there are also cases when I don't have that redirect, and therefore I'm also a victim to a denial of service attack. Okay, so that's rogue route advertisement. You have a rogue router here, making fake advertisements within your local network. Another command or tool that's used for that is the fake router or fake router 26 command. And as you can see from my output, what happens is I'm announcing a prefix. So if I look from the victim side, okay, you have here, there is an injected IPv6 address using the prefix that I announced. So in my command here, I'm using 2001D35DB33F. So notice here, I now have another IPv6 address with that same network prefix just by using this very simple attack. Alright, so we have more. Okay, this is for the same command, I think, but this is what happens from the attacker side. Okay, I'm just sending a lot of packets out there. So notice it says a dot is printed for every 1,000 packets. So imagine how many packets I've sent out with this. Every dot is 1,000 different packets. And what happens on my victim side is, okay, I have this IPv6 address. I can have a lot of IPv6 address because we know that in IPv6, an interface can have one or more IPv6 addresses. So you don't have the limit of only having a single one. So if there's an attacker announcing multiple prefixes out there, you can use them. You can be assigned an IPv6 address on your victim machine. So those are just some of the examples that I've shown you. Hopefully, okay, it showed you that yes, these types of attacks are actually possible and they are happening. But the question here is, for us, if we're maintaining networks, if we're in charge of our networks and we're going to implement IPv6, should we be worried about this? Okay, what are the security, security things that we can do, okay, we can implement to address this? Now, the good news is, okay, rogue RAs or neighbor discovery spoofing attacks, a lot of, well, not all, but there are intrusion detection systems should now be able to detect them. Okay, obviously your IDS or IPS will be able to learn it as you go on because it needs signatures to be able to do that. But if you have them running, okay, you have some sort of assurance that an IDS should be able to detect those types of attacks. There are other tools that have been available out there. This one, NDP has been available since early 2000, I think, or 2010. And not sure if it's being updated now, but you can get this from SourceForge. It's an open source project. But there is a corresponding RFC that discusses this one as well. There are others such as RA1D and then RA6D, so you can all look them up as well. Now, what else can you do? There are standards that are available that have been published as a either as an informational or as a standard. I think these next two are all standards, meaning routers should be able to implement this based on the RFC. One of that is the RA guard or the router advertisement guard. So from its name itself, you can say that the idea behind it is obviously to filter out, okay, all those fake ICMPv6 router advertisement message that are not coming from the correct source. Now, the main idea, and you will see that in the slide after this, is the basic solution, not the basic, the optimal solution for protecting or for implementing solutions for IPv6 router or neighbor advertisement NDP issues are to use what they call as SEND, or secure neighbor discovery. Now, however, this type of solution is not really very trivial to implement or to deploy. So the idea behind RA-Guard, okay, is to provide you with a lightweight solution, a lightweight alternative to send that can be implemented on a layer 2 device. So it is done or on your switches or your multi-layer switches, and it will filter out RA messages based on a set of criteria. Okay, so you as an admin, you can specify what those criteria will be, and then from there you do basic filtering. Say for example, if you only want to receive RA messages coming from a particular port on switch, you can do that. Okay, as far as I know, Cisco obviously can implement that. Most other managed switches should also be able to handle that. But so basically the idea with RA-Guard is that there are different types of RA-Guards that can be implemented. It can be stateless, stateful, or send-based. So with stateless, you're filtering RAs based on the information that you find on the message. Things like the source address or the prefix list, or the you have set of route priorities. And then on a particular switch port, you can specify them to check for those particular kind of like messages and then filter it out accordingly. Another one is stateful RA-Guard. This one is a bit more dynamic because it learns from all the interactions, from all the IPv6 messages that it gets. It will find legitimate RAs based on who's sending, what type of packets are getting. So it's basically in a, what you call as a learning mode. It learns these sources, prefixes, and implements filters accordingly based on what it learned. And then the last one, I mentioned a little bit about send. So this is send-based RA-Guard, which does the filtering again on your layer 2 device, but this time based on your send considerations. So you can all look those up and implement which one is best for you. Now, what about send? What is send? So now the original NDP specifications actually called for the use of IPsec. So we know that IPsec is part of IPv6. And how are we going to protect NDP messages? We can, of course, use IPsec for that particular purpose, right? But in a lot of the standard specifications, there are no detailed instructions on how to actually use them and implement them. So with send or secure neighbor discovery, it's somehow takes a few of those that you can probably implement in just IPsec. It uses crypto, so you are essentially securing the entire NDP message. It uses certificates and all of those things, and it has different neighbor discovery options that can be implemented according to this. So all NDP functions, obviously we will be using RS, RA, NS, or NA messages. Okay, you will still be using the same stuff. The NDP message will still follow using that ICMPv6 message format. But send will introduce a few neighbor discovery options that can be added according as part of the ICMPv6 packet, right? And the purpose really of these neighbor discovery options is to protect your NDP message. So that's pretty much what you will have there. I won't go through the details of send, but just to let you know that it's out there, it's available. If you want to implement this in, say, your Cisco machines or other types of routers, you can do so. I don't have the specifics here, but you can just easily search for the documentation on how you, or what commands to use if you want to implement send. Any questions so far? I noticed that a few people joined us quite belatedly. I will be saving up the video for this, and I'll share those video later on for you to view from the very beginning. Okay, now we've talked a little bit about the route filters, send and route filters, RA filters or route advertisements. We talked about send, so those are standards and you can implement them in your machines, right? Now, what else can you do? We can use filters. Now, from this point and forward, this is actually a lot similar to what you do or what you implement as a best practice in IPv4. I always say this to people that if you have security in IPv4, you somehow already know what type of IPv6 security you will have in place. Okay, that's a bit generic, of course, because you will still want to cater for, say, what types of traffic you're using for V6, what types of ports are available, what about the IPv6 messages that are being sent out, things like that. You have to consider them. And those things differ. We've tackled some of those in the first few slides of this course, right? But a lot of things like, particularly if you're a service provider or a transit provider, is to perform or is to provide filters. Once you implement IPv6, make sure that there are filters in place. So whatever security that you have in IPv4, it doesn't have to be point by point the same, but you use similar ones in IPv6. Okay, what type of types of, say, ports are going to be available, what types of source addresses and destination addresses and things that should also be implemented in IPv6. You will have to filter out some ICMPv6 messages, but you have to be very careful. Not all should be filtered out because ICMPv6 is very important in neighbor discovery protocol. You may want to do rate limiting as well. Okay, I think I might have an example of rate limiting a little bit. Let's have a look. You will want to block routing header 0. That is if you're still implementing older versions, because right now with the current standard, current RFC and RFC 5095, this is now already default. This is the reason I did not discuss about routing header 0 at the beginning as a possible security issue is because it should not be an issue anymore because it should be implemented by default. However, if you find that that's not the case for you, you may want to use the no IPv6 source route implemented on your intermediate nodes so that you won't have any IPv6 packets that are using routing heading 0. Okay, and BGP route filters. Obviously, that one is very important, similar with IPv4. Let's just look very quickly at some of the ICMPv6 messages and which ones should be allowed, which ones should not be allowed. In here, in this link with Ayana, you will find a list of all ICMPv6 types and their code values. Some of them are used, some of them are not, some of them have been allocated. So some have like different purposes, right? And you will see that in RFC 4890, have a look at that. This is a good thing to read. It gives you a recommendation on how you can filter ICMPv6. I just have a few here, but if you want, you're more than welcome to read through the entire RFC yourselves. So what are the things that should be blocked? So most of the red ones here are suggested to be blocked. Okay, undefined types. Okay, type 5 to 99, 102 to 126, unallocated informational messages, experimental messages, and extension type messages. So these are usually stuff that you wouldn't normally find in your network. Okay, so it's okay and it's best to just filter them out. These messages should also be blocked through the network perimeter if you're not using them for a particular purpose. Okay, if you're the admin and you think, oh, I'm not going to use this anytime soon, just block them. That's type 138, 139, and 140, and type 129 for echo reply. However, some ICMPv6 messages should be allowed by default. Okay, as I've said, some of them are used for legitimate purposes. Things like these types must be permitted through your network perimeter. Destination unreachable, packet too big, time exceeded, parameter problem types. They're all important because they're kind of like responses to possible errors in the NDP packets that you're sending out. Type 128 and 129 for source and destination. These are basically for pings, echo request and echo reply. I think should be safe to be allowed. If you want to do restrictions, you restrict it to particular, say, subsets of your network, but it should be generally allowed. Now, how can you use those filters? This is an example, and I think this is implemented in a Cisco router. This is using rate limiting for ICMPv6 traffic. So if you're concerned about overwhelming your router, you can do this. So what we did was we created a policy map. This is your policy map, okay, class ICMPv6, and what you're going to do when it reaches the limit, this is the action. The exceed action is to drop. And then you create your class map, match protocol IPv6, match access group name ICMPv6 essentially for your policy. And then you specify your policy as permit all ICMP traffic here and implement that onto a particular interface on your network device. So you can do a similar one. Okay, maybe you will have a different policy type, but essentially you will want to follow the same format. Just grab the link to the survey. Again, this is very important to us, particularly now, because this is the first time that we've conducted this course. So if you have anything that you want and we have not covered it here, this is your chance to tell us about it. So that's the link to the survey. The handouts are going to be available. I don't think you'll be redirected automatically to the FTP page right now, but I'll just give you the link to the FTP here. Alright, this is a link to the FTP where you can download a copy of the presentation that we have for today. It's in PDF. So have a look at that. And if you still have issues, let me know. Confused with the time zone. Yep, apologies about that. Time zone is GMT plus 10, which is Brisbane time. I think that's why we don't have enough people when we started this session. So what we can do for you guys is I can share you the recording of this session. Okay, I'll send an email later on with the link and you can play back this session. We will also be conducting this session a few more times in the future, so you're free to attend that one as well. But yes, I will send you the link to the videos a little later on. Alright. Any more questions or feedback? If not, I think that's where we will end this session. Thank you very much, everyone, for attending. And hopefully, I will see you again in another e-learning session. I can read your chat, and I'll take all of those things into consideration about the time and those issues, and we'll try to sort them out. Again, thank you, and I hope you have a nice day. Bye-bye.